this, this is actually a sample of the simple quantum gas system, as we talked before. So this is an example of the grand partition function for this system is n1 plus 1 minus z. So today we want to find just the partition function and pressure, and also we want to find the relation between n and the other parameter of the system. So if you combine all together, you will get the real equation of the state for this gas, because this gas doesn't have this equation. That was just for the ideal gas. So for the bosonic gas as a real quantum system, so you needed to evaluate this and evaluate that and eliminate the parameter and get the equation between PV and N. So far we don't know what's the relation between them. So the aim is that to find these two sigma. So if you can evaluate these two expressions, then you can find the equation of a state. You can find the pressure in there. So this energy is here is started from the zero. For bosonic system, boson's energy is always positive. So the things which we will do is that first we separate the contribution for the E0. So we consider the E0 as a special case actually, plus the other ones which they have the energy greater than 0. Because you will see that here the number of the particle which is given at the energy E0 have a different behavior than the number of the particles in the excited states. So let's exclude the terms with E0 here and here to see what happened. So PV over KT will be minus ln1 minus z minus and the same will be for that. Similar actually will be 1 over z minus 1 minus 1n plus sigma n is 0 n. You need to do this calculation, otherwise you cannot find the expressions for the pressure and the. What is that? This is the, as I told you, this is the contribution of the n when it is 0. So in the bracket, so we have n0 z over 1 minus z. So from here you can find z also. 1 plus n0 z will be n0, so z will be n0 1 plus n0. Keep it as a question for the future. Just it gives you the z in terms of the number of the particle in the ground state. And I know how to calculate that, but let me to just work at the first term of this and keep it just for the later. So when z is n0 over 1 plus n, I want to substitute that here, just here on minus ln. What will be 1 minus z? will be 1 over 1 plus n0 minus sigma b0 ln 1 minus z minus beta. And here, as you see, it will be just n0 plus sigma a. And this is, as I told you, that's all the number of the particle in excited states. The state with their energy is greater than or larger than the energy of the ground state, and this is the portion of the particle, the number of the particle can sit in the ground state. So still we can simplify these two equations. PV over KT will be ln 1 plus n0 minus sigma E. And the n minus n0 will be sigma E 1 over z E beta E. So from this equation we will keep it that just. We will keep it that, and we needed to calculate, to be calculated. And for here, I will divide that by the V just. So P over KT is ln 1 plus n0 over V minus sigma 1 over V ln 1 minus z minus beta. So I want to evaluate these two expressions, this and this. And the main interest is that to see that what will happen for this expression when z will goes to the 1. Because from this equation you see that z will be always between 0 to 1 from this equation. It's trivial because n0 is a positive number. This is n0. It's a positive number. So z will be bounded between 0 to 1. So when n0 is 0. So when 0. So this is the graph for the z actually versus the n0. So it never can be never exceed the 1 here. The maximum will be 1. And it happened for the case when n0 is near to infinity, or n0 is very big, large number actually. Yeah, from the graph you will see. Exactly the point which z tends to the 1, and when the n0 becomes larger than any other n, and this is a possibility that something happened here, it will be some critical point. It's very strange. The system after and before that have a different phase. This is only in the boson system, and when you have the massive boson. When you have a massless boson, what's the example of massless boson? Photon, for example. For photon never happened that. For photon, this condition never happened, so you don't have the Bose-Einstein condensation or critical point for bosonic gas, for photonic gas. You will have only for the massive gas bosons. Massive boson can be any particle, any boson with the mass non-zero mass. So for photon never happened that. For any bosonic system it happened, these situations. But it depends that what's the value of n0, what is actually is a big number. It depends to the mass of the particles. So this this N0 and this phenomena is happen when the boson have mass, only for the massive bosons. Not for photon, for example, it never happened. But the question will be, for example, they will ask you one day in your life that Bose-Einstein condensation happened for any of the boson types, so you can say no for, because it needed to have the mass. So we needed to calculate these integrals. So sigma over the energy can be transformed to the integral over energy if you have the density of the state here, and because this is start from 0, what I should put it here as an upper limit. Upper limit I can put infinity. What about the lower?
0 plus. It's 0 plus.
Yeah, 0 plus, because so it started from here because it's not 0, it's just a little bit far greater than the 0. So what about the GE? So for non-interacting and non-relativistic simple case bosons in a box with volume or enclosed the volume V, for these situations you can write the expression of GE like that. GEDE will be 2P, this coefficient 2PVH cubic 2M. I will tell you how to find it that. There are different ways to find this AE. One is you can back it and then, but GAE was exactly the omega E in the first chapter. You can see the expression of the omega E for the particle in the box. So it was proportional to the energy. Do you know how to find that? You know the energy of the one particle in the box was P dou H equal to 2M L square NAX square NY square plus Z square. This is in the bracket. This is the oldest method to find this. So if you find NAX plus NY plus NZ, it for the given energy, it was 2M E V, because L is V cubic. So I can set it as 2/3 P dou HY square. Things is that this is actually defined in S sphere. This is a sphere actually in the NX and NZ coordinates. So the radius for that, the radius for this is this. This is R square. R square is proportional to the EV2/3. So R is actually proportional to E power 2. But this is not the only things you needed. We needed also to. But I wanted to do that. From here you can find this AE. But I want to tell you one more method. This is not because it needs to find the volume of this. The best way is that the best way will be maybe the things which I will tell you now is the best way to find AE. GAE, the E, is the number of the particle with energy between E and E plus the E. Yes? These particles are exactly the same as the particle which have the momentum between P and the P plus delta. So it will be the same as the number of particles with momentum P to P plus delta. You understood that this GE is related to the volume, to the counting of the state which they have the energy E, number of the particles with energy. We needed to find that how many particles have this energy. It's related to the volume. So number of the particles with momentum is also given the volume. So this is actually the volume of the sphere when the momentum is between P to P plus the P. So this is the momentum. I needed to set the normal volume here. You know, delta P delta Q is still h bar s squared, so the unit for the phase space, I want to tell you that delta P delta Q or Q delta Q is in the order of h bar or h. So if you want to write the expression, this expression gives you just a number, so it should not have any length, any cubic length, volume, area or something. It will be dimensionless. Still you have L cubic here, you have P cubic here. So L times to the Q to the L times to the P will be in the order of H. I needed to make it this dimensionless, so I can put it with H cubic here. And let's to go and define. Maybe there is a coefficient we needed here. Well, let's to see. I want to find the GAE. So GAE will be, look, GAE will be V chart this H dP dE. This is it. So you need it. This is general. This is very general. For relativistic, non-relativistic, for anything, you can use this expression. The difference will start from here. What is the relation between energy and momentum? This is called a dispersion relation. You needed to know that what is the dispersion relation for your gas. Yes. For non-relativistic particle in the box, E is P squared over M. So P is radical 2ME, root of 2ME. So dP dE will be radical 2M E minus 1 over 2. So GAE will be, I told you, we needed to finally to see that for P, the coefficient is important. What is the P squared? P squared I can write 2ME, radical 2M, E minus 2. So let's to see what we find.
Shouldn't have to, right? differentiate with A.
Oh, that's, that's true, that's true. When we make a differential, we will have 1 over 2. So that was the factor which I was looking for. So 2 by 2 cancel, so 2 PV H cubic. Yeah, this is the, so we derive this. We derive that. So this is a GAE. But remember, this is a very important equation for any system you can use it. For example, if I give you the relativistic gas, you needed to know that what is the E versus the P for relativistic gas, and you can get it at those calculations. For ultra-relativistic gas, for example, E and the P are linear. E is PC. So you can still. But this is the GAE. So when you have a GAE, you can evaluate your integrals. So now I want to evaluate the integrals.